Hey everyone, and welcome back to the channel. Today, we're blasting off to the Red Planet to uncover a story written in stone, a story that's billions of years old. We're heading to Mars's Jezero Crater, the landing site of NASA's Perseverance rover. For years, scientists have looked at this crater from orbit and thought its floor was made of sedimentary rock, laid down by an ancient lake. It made perfect sense, right? A giant crater, evidence of a river delta flowing into it. You'd expect a lake bed full of mud and silt. But what Perseverance found on the ground has completely flipped that idea on its head, and it's way more exciting. Imagine this. You're the Perseverance rover rolling across the crater floor. You extend your robotic arm, use your instruments to get a close-up look at the rocks, and what do you see? Not the fine-grained, layered sedimentary rocks you were expecting. Instead, you find coarse-grained igneous rocks. That's right, volcanic rocks. Specifically, the rover discovered rocks composed of large olivine crystals, a mineral that's very common in magma here on Earth. This discovery was a huge surprise. The rocks looked like they had formed from cooling lava, not settled out in a calm lake. So, how did scientists figure this out? Perseverance is equipped with a suite of amazing tools. Instruments like Pixel, which is essentially a super-powered X-ray scanner, mapped the chemical elements in the rocks. It revealed these large, well-formed olivine crystals embedded in a matrix of other minerals. On Earth, this texture is a classic sign of a rock that crystallized from a slowly cooling body of magma. Think of a thick lava flow or a magma chamber deep underground. The slower it cools, the larger the crystals can grow. The rocks in Jezero Crater, particularly a unit scientists have nicknamed Seita, which is the Navajo word for among the sand, were full of them. This was the first major clue that the crater floor's history was fiery, not just watery. But wait, it gets even more interesting. If these are volcanic rocks, does that mean the whole lake theory is wrong? Not at all. This is where the story gets layered, quite literally. What the rover's findings suggest is that the volcanic activity happened first. After Jezero Crater was formed by a massive impact billions of years ago, its floor was filled with volcanic eruptions and lava flows. These igneous rocks formed the very foundation of the crater floor. Then, later on, water arrived. It flowed into the crater, forming the lake we've seen evidence of for so long. This lake then deposited sedimentary layers on top of the volcanic bedrock. And we have proof of this interaction. The rover found that these volcanic rocks have been altered by water. The olivine and other minerals show clear signs of chemical changes that could only happen in the presence of liquid water over long periods. Perseverance detected carbonate and sulfate minerals, which are classic byproducts of water interacting with rock. This tells us two things. One, the volcanic rocks were there first, and two, they were submerged underwater for a significant amount of time. It's like finding an ancient Roman coin at the bottom of a medieval well. The coin tells you about the Roman era, and its position in the well tells you the well was built later. Here, the volcanic rocks are the coin, and the water alteration is the well. This completely rewrites the timeline of Jezero Crater. We now have two distinct and important habitable environments to study. First, you have the subsurface environment within the cooling volcanic rocks. Even as the lava cooled, fractures and pores within the rock could have been filled with warm, mineral-rich water, creating hydrothermal systems. On Earth, these are fantastic places for life to begin and thrive, protected from harsh surface conditions. So, we have this potential for life deep within the rocks themselves. Then, you have the second habitable environment, the lake that came later. That lake, which deposited the famous river delta, could have hosted a completely different ecosystem on the surface. This is a game-changer for the Mars sample return mission. Perseverance isn't just looking, it's collecting. The rover has been drilling core samples of these very rocks. We now have pristine samples of ancient Martian volcanic rock that has interacted with water. Getting these samples back to Earth will be like unlocking a treasure chest for planetary scientists. In labs here, we can date these rocks with incredible precision. We'll be able to say exactly when the volcanic activity occurred and for how long the water was present. Was it a brief flood or a long-standing lake that lasted for millions of years? The rocks hold the answer. Furthermore, analyzing these samples will allow us to search for biosignatures, telltale signs of past life. Could microbial life have existed in those warm, watery cracks within the volcanic rock? By studying the specific minerals and organic molecules locked inside these samples, we might finally find out. The discovery that the crater floor is igneous is, in a way, even better than if it had been sedimentary. Volcanic rocks are like geological clocks. Their radioactive elements decay at a predictable rate, allowing for very precise dating. Sedimentary rocks are much harder to date directly, so these volcanic samples will anchor the entire history of Jezero Crater to a solid timeline. Think about what this means for our understanding of early Mars. We now have definitive proof of a volcanically active period, followed by a watery period in this one location. This complex history, with multiple types of habitable environments, makes Jezero an even more compelling place to search for life than we already thought. It wasn't just a simple lake, it was a dynamic geological system, alive with volcanic heat and flowing water. It was a world of change, and change often creates opportunities for life. The story of Jezero is no longer just a story about water. It's a story of fire and water, a powerful combination that could have cooked up the perfect recipe for life. The work of perseverance is a testament to why we send rovers to explore. From orbit, the crater floor looked like one thing, but the ground truth revealed a far more complex and fascinating reality. It's a powerful lesson in science. You have to go and look. Each drill core, each chemical analysis is a word, a sentence in Mars's ancient autobiography. And by bringing these samples home, we'll finally be able to read the full chapter on Jezero Crater and maybe, just maybe, find out if we've ever been alone in the universe. What an incredible time for discovery. Thanks so much for joining me on this journey to Mars today. If you found this as fascinating as I did, be sure to hit that like button and subscribe for more deep dives into the cosmos. Let me know in the comments what you think about this fiery twist in Jezero's past. Until next time, keep looking up.